All right, it looks like we are now live here, I believe. It's great to see everyone. I know it's been a little bit since our last stream here, but I'm super excited to be back. Been traveling a little bit and just had lots of stuff going on, so definitely missed doing the streams, and want to make sure that we're doing these pretty regularly. They are, both an opportunity for me to hopefully share some insight into some various aspects of building a CPU and building our kind of top to bottom computing system, really. But also, it's just a nice kind of like cadence to hold myself accountable in building this, because I have a lot of other stuff going on and I'd love to commit more time to it. But these streams really kind of help keep me making sure that I'm kind of driving this project forward, which is definitely really important. So thank you for watching this later or for being here today. I think we're going to have some good fun. We're going to be getting back into some simulation, which I haven't done for quite a while now. And so I'm going to need to brush up my skills a little bit. So I think this is going to be maybe a bit of a painful stream, but we'll definitely learn quite a bit. And as always, we'll document everything we do. So the next time we do it, we can quickly refresh on it, and we can also share out our notes with other folks. So let me go ahead and drop a message in the chat here. I just put out on Twitter. And then I am also going to get set up to stream from my dev machine over to this one so that y'all can see my screen. All right. And last thing here, to open up OBS over here. And we'll keep this in the background. All right, it looks like things are coming through here. Nice. All right. So let's go ahead and jump into it. I'll switch over to split screen here. All right. So last time on our last stream, we were looking at adding our UART receiver. So we had a UART transmitter. So we were able to send from our from the FPGA, which I actually just realized that I don't have this on my desk, so I'm gonna have to go grab that in just a minute. But we were able to send something from our FPGA over to our dev machine here. So let's see if we can take a look at the diff in our transmitter here. Yeah, so we need to remove this. But previously we were sending welcome to the MOS computer with a carriage return here, and that was showing up via the serial port on my dev machine, which was cool to see. But what we wanted to get to is having a UART receiver, and our kind of initial use case for that was going to be to send a message from my dev machine here, and then echo it back. And so we couldn't quite get that working. We were able to see data coming in, but we weren't able to echo it back. Basically, the way this is working is it's reading data coming in, and once it kind of sets all of the data wires, these output reg here, so it sets the 8 bits coming in, then it sets send high, which in theory, what we're going to be doing here is having when send goes high here, or we're calling it, let's see, yeah, send. When send goes high, yeah, here we go. Then we're going to start reading from those data wires and sending that information over to the dev machine. So sending it out and then getting it back. And before we get too far into this, I am going to go and grab the FPGA real quickly. So I will be right back. All right, so I got it here. It's in its box. I recently, and I just realized that I'm also going to need to go grab the cord here in just a second. But I recently took this over to Hardware Happy Hour in the Research Triangle area, which Chris Gamble organized, and was able to meet a lot of cool folks doing hardware stuff in kind of the Research Triangle area. So that was really cool. So I took my FPGA there. I wanted to talk about MOS a little bit, and I also heard about a lot of their really cool projects. And I am going to go ahead and go grab that cord real quick as well. Alrighty, so I just brought my whole bag down because I'm not actually sure where I put this. So we're gonna see if we can find it here. I think I took it with me, but it's not in this bag. It doesn't appear. Alrighty, let's see if maybe I have it. Aha, found it. Sorry for the interruption there, but it looks like we got it. Actually, we got two of them here. So we're all good to go. drop those back in, and we'll keep them on hand here. Nice, we'll just use the shorter one for now. All right, so we're all set. I can also switch over here. I'm going to go ahead and plug this in, and then plug the other side into my machine here. All right, and let's see. You can see that we're lighting up now, and should be good to go. Cool. Alrighty. So I am a little scattered on the Saturday, but I think we're all set now. And I am going to open up our code base here, and let's get to it. So basically, we were kind of flashing this onto our dev board and trying to run it, and weren't getting the results we wanted. And obviously, that's not a very sustainable workflow. So we want to go ahead and get some simulation in place. And so we are going to be using Verilator, which is a popular tool for simulation of Verilog, and I believe it supports system Verilog as well. And we're kind of just going to go through everything. And we already have kind of the machinery set up on the repo. So if we hop back over here, had an issue with things closing on me here. Let's see if that'll pull back up. If we hop back over to the repo and jump into Sim, you'll see that we have kind of like just the scaffolding for this. We also have it for our ALU, which we haven't talked about too much yet. And we have our GitHub workflow, which just runs Verilator, which basically translates your Verilog into a C++ library, and then you can write your code to kind of wrap around that and execute some things. And we'll look at the output here, and then you can execute after you compile your wrapper around it. All right. So let's look what we have here. We have our sim directory, and I have also moved to using NeoVim for my editor. I'm still getting a little used to it, but have really liked it so far. So if you are a NeoVim fan, that's what we're going to be using today. But before we jump into the sim directory, let's take a look at our make file actually. And let's look at our Verilate target. All right, so we have Verilator set to our Verilator binary we have installed. And we check, and when we run Verilate, we check and see if our object files have changed at all. And then those are based on the simdir, which is the it's called sim in this case. So if we change the wrapper around either one of or any of our C++ files in the simulation directory, or if either of the Verilog, or if any of the Verilog files change, which I'm not sure why. I don't remember what the diff was for here. Actually, let's take a look at that. Yeah, so I added the UARTX, which the previous one should match to any Verilog file, so we can double check on that. But we basically run Verilator, generate the Verilator headers and library, and we enable some of the flags here, which we can look at in a moment. And then yeah, and then we run them. So let's see if this target is working correctly. All right, so it doesn't like something about our top simulation. So obviously I have some stuff in here that doesn't match what's in the Git repo. So let's jump over to that. All right, so in the main here, I've done some setup, and you should be able to see the Git diff here with Git Gutter installed. Number one thing I want to change about this theme is that my line numbers there on the side are extremely faint, at least for me to be able to see. So I'd like to be able to adjust that. Maybe we'll do that at some point on this stream as well. We initialize the arguments, so just pass those in from our main function here. And create an instance of vtop, which is what Verilator is giving us, which is kind of like the representation of our top Verilog module. Setting up to write a waveform here. We'll talk about this a little bit more. I also need to refresh on it a little bit. And then essentially what we do, and this is a little stale here, but we're just going to go through and manually tick our clock signal. So this is just a member on the this vtop struct, right? Because in our, let's actually just look at top.v here. We have our input clock there. And so we're basically just manually able to drive this as opposed to it, coming from a signal coming in to our dev board. And all of these are going to be members of the top module struct. If you haven't already noticed, I'm not a C++ expert by any means. I would like to improve on that side. I've mostly, I did a little bit of C++ in college, have written some C, so, that's helpful as well, although C++ feels infinitely more complex. And I've done a fair amount of Rust, but yeah, C++ is still a little bit of a mystery to me. So let's go ahead and look in our object directory, which is what Verilator is creating. So it generates all of these files here. And we are bringing that vtop header file. So let's take a look at that. So we have our local signals. We have our ports. So our clock here. Yeah, so it actually helpfully annotates a lot of this for us. So the application code writes and reads these signals to propagate new values into out from the model. So basically it's saying like we've synthesized the model as a C++ module or object here. And then you can, manipulate the signals coming in and out as you see fit. So we have these local signals as well. Once again, this is going to map pretty directly to what we have. So we have data send and RX and TX state there. And you can see like it tells us even what the width of those are. So yeah, we have the data, URTXT in, et cetera, et cetera. All right. Let's jump back over. Construct the model. So that's what we're calling there. Trace signals in the model. And then eval is what gets called after we modify the various variables. Then we call eval, and it kind of evaluates at that point, kind of as you would expect. Cool. And I don't know too much else about this. So actually, I wanted to look at the object. So let's look at our vtop .cpp there. Oops. So we can see the implementations of those symbols from our header file. So we have eval step here. And you see we have some conditionals based on if we have debug set. Let's see what else. Eval initial loop. Yeah, and there is a lot going on in here. So we might have to dig into this a little bit more in a moment. But it's basically, what you need to know is that it's simulating our model here. So let's actually get some stuff going and then come back to this, and we'll also dive into the documentation a little bit. All right. I'm gonna clean up a good amount of this. We don't have the switch anymore. And I'm going to clean up that comment. Let's see if we can just go through and tick this a little bit. Okay, so here we're saying we're going to go 1 to 100 ticks of our clock here, and we're going to need to look at what our baud rate is to understand how much we're going to need to tick this, or how we can modify that, which we're going to want to do with some parameters. But we're saying the clock equals 1 minus whatever the clock was previously. So if the clock starts out at 0, then we switch the clock to 1. And then if the clock is 1, right, then we go back to 0. So we're just flipping that. And then we're also writing to our data.vcd here. And we'll talk about that in a minute. But all right, so we were able to verolate successfully, which means that our object directory has our vtop and valu. So that's actually what gets run. Let's see. Simulate. So I need to say make simulate dot top, I believe. All right. And we can't really tell anything happening there, but let's go ahead and remove our VCD file. And we should take notes on all of this, of course. But let's just get through one run. Make simulate.top. And our data.vcd is back. So it is running successfully. And we have some information here. This isn't really going to be useful to us quite yet. But we can go through and kind of look at what is happening here. All right. So let's take a look at what we have in the way of developer docs here. So we have testing and simulation that talk about all the things that I went through here. And a lot of this isn't quite set up yet. But I don't think we have anything on just Verilator. A lot of this isn't pushed, so I want to definitely do that at some point. So we have our Vivado docs here. We have Verilog. Let's see how these are structured right now. Right now we just have them all in here. I feel like these are really kind of more like learn docs. But let's just do Verilator in the main docs directory for now. And we can go from there. I think in our last PR, we did introduce that dev directory. Getting some phantom clicks here, it seems like. Yeah, so we introduced this under serial. So yeah, maybe Verilator makes sense to go in there as well, right? It has to do with developing. What do we have in Vivado? And let's create this file. So docs dev, and we'll call it verilator.md. Verilator. We'll save that. And let's get into some documentation here. So I have this up. And we can take a look at the Verilator site, and we'll probably want to link to that as well, which is how I got to this PDF that we have up anyway. And I want to see if we can follow the same structure that we have in the JTAG. Which one? Docs, JTAG, yeah, resources, okay. And we'll say docs, dev, Verilator. All right, so we said resources, Verilator website. And let me grab that link. All right, and let's talk about an overview. So this is probably a little small, but it says it is the fastest Verilog / system Verilog simulator. Has a section on what Verilator does, and has some notes about performance, which we're less interested in right now because we have a pretty small design here. but I'll just read it quickly because I want to for my own sanity here. It says Verilator is invoked with parameters. Here, let's make this bigger. Verilator is invoked with parameters similar to GCC or Synopsys VCS. It verilates the specified Verilog or system Verilog code by reading it, performing lint checks, and optionally inserting assertion checks and coverage analysis points. It outputs single or multi-threaded C++ and header files, which it refers to as the verilated code. The user writes a little C++ system C wrapper file, which instantiates the verilated model of the user's top-level module. Yeah, so that's what we were doing, initializing vtop. Yep, and then we compile with the C++ compiler, and executing the resulting executable performs the design simulation. Verilator also supports linking verilated generated libraries, optionally encrypted into other simulators. Cool. So we have also this Verilator manual here. And I love to get into a good manual. And it has some breakdown of some of the flags that it's passing. So W all, so we want all of the lint warnings enable. We want C++ output, so that's -cc. Let's take a look at our make file. All right. So we're saying we want W all -cc. And let's jump over here and just say Verilator is a tool that translates Verilog into, and what did we say? Translates translates Verilog into a C++ model that can be invoked to simulate Oh, I also realized my face is over part of this. Verilator is a tool that translates Verilog into a C++ model that can be invoked to simulate the RTL design. And yeah, we'll just leave it at that for now. Configuration. Configuration values. Those used in MOS are detailed below. So let's say W all turns on all Verilator linter warnings. Let's see the other ones we had here. -cc specifies that we want output in C++. All right, and And are we passing exe? Yep. So we're doing this kind of all in one go. So we're saying generate the C++, um, and also generate an executable. Let's see if this might be actually a better path to go through here. Argument summary. Let's see. -exe. Link to create executable. So we're saying that we want to both generate the C++, and we want to pass our C++ for it to be able to build. So I'm interested in, let's see, build model executable / library after variolation. And then exe is linked to create executable. So I wonder what happens if we only pass one of exe or build. Let's see if it okay, yeah. So along with our sim main wrapper file, so the build will create an executable instead of only just a library. -- build, so Verilator will call make itself. This is so we don't need to manually call make as a separate step. You can also write your own compile rules. Cool. So it looks like whenever I added this that I had been looking at this for sure. So we'll go ahead and write those down. So ESC specifies that we want a executable rather than just a library, and -- build. We don't need to manually call make as a separate step. Because it generates its own makefile as well here. Let's see if we can go into object directory. I think it generates its own makefile. Maybe not. So maybe exe is saying we want an executable, and build is just saying to build, right? So it's not necessarily saying that like if it was just a library, right, it would also build it. So it's building the executable. If we didn't pass build, I'm not exactly sure what would happen, but let's actually give that a try. Oops. There we go. So I'm going to remove our object directory. Let me make this a little bigger. And let's go over here and say that we don't want build. We just want Oh, that vtop.make. Okay, there we go. So it's specifying we want an executable. So I think if we don't pass build, right, it's not going to build the shared library or executable or whatever. But if we pass build and actually, let me just add that back, and not executable, then we should just get we really need a clean target here as well. Oops. Make verolate. Yeah, so if we compare this to what we had before, so we have our object files. And in the last one, yeah, we were missing our object files. Cool. Okay, so that makes sense. Maybe that was obvious to everyone. If so, apologies for the delay on my end there. Let's add that back. All right. So if that's ever not obvious for someone in the future, at least they'll have something to take a look at. And let's look at vtop.mk. So yeah, we can see that this generates a file here. And default vtop all.a, verilator root. vtop classes.mk. Okay, so I think that it is probably in here somewhere that we have our actual targets, maybe. Oh. vtop.mk verilated makefile include global rules. Okay, verilator. Okay, so it has some here. So we could actually take a look at that, but we'll not do that right now. But basically, it's going to build our executables or objects. Also, shout out to whoever just joined the stream there. All right, so let's take a look back at our makefile. So we have our targets. We're saying if these change. I don't want this in here. Don't remember what that was added for. So we're saying if any of the C++ files change or any of the Verilog files change, then we want to regenerate our Verilog, or sorry, our verilated code. Verilate just does that for the top.o and the object files for top and ALU. All right, and simulate calls each of those. Okay. Oh yeah, and it doesn't like that. Simulate.top. Make simulate.alu. Okay, so both those are working. let's close that out. Okay, so we have these flags. Oh wait, we also had, what did we say? Trace. Shouldn't have closed that. Let's see. Make file. We also have trace and -I, which is just telling where our RTL lives. But in the spirit of documenting, let's go ahead and make sure to put them in there. So man var_later. Make that a little smaller. Trace. Enable waveform creation. Yep, so that's what we want. Enables waveform creation. And what was the last one we had? We had, -I. And we probably don't need to look this up, but let's see what it says. -I CY. All right. Sets. Adds directory to the list that var_later searches for RTL. All right. So I think that is pretty helpful there. Let's close that for a minute and look back at our sim. And we're just looking at top. We haven't looked at our ALU at all. Also, just maybe like stepping back for just a second. The reason why I'm focusing on the UART initially is in the kind of like mission statement for MOS is that we want to build a computer that's exceedingly understandable by users, but still like realistic in that we're trying to make it performant. Because honestly, like, yes, performance is a goal of this in general for things that we want to run on it. But also just because, it's not supposed to be a toy, right? We want to be able to actually interact with the concepts that are in modern CPUs today. But being exceedingly understandable by users, having the UART in place is going to allow us to communicate. So anything we build after that, or including the ALU, which we've already built a little bit of, is going to be, interacting with it is going to be easier. So, all right, this looks good. And this is system C. We already have it installed. Build. Oh, it comes in a Docker container. That's useful. Verilating. Okay, so it reads input Verilog code, determines all top modules. That is, modules or programs that are not used as instances under other cells. If top module is used, that determines the top module and all other top modules are removed. Otherwise, a multi-top warning is given. It writes the C++ code to output files in the mdir option specified directory or defaults to object directory. The prefix is set with prefix. Okay. Well, this is helpful. exe and build are explained right here. And that's why you read the docs, folks. don't care too much about multi-threading right now. All right, let's see if we can actually just get into doing something interesting. So I'm going to try to add a printf in here that just tells us something about the current state of things in the module. So, and I don't have NeoVim set up for completion here, so this is going to be a little painful. But we'll have some fun with it. All right, so we'll go up into object directory, and let's take a look at vtop.cpp. Actually, no, we want vtop.h. All right, so we have our clock. What we really want to see is clock count, bit index. So I think what would be most useful is for us to write something to the receiver, and then see how that changes like the state, for instance, in the receiver. Yeah, so this one, the state would be interesting to see. Let's split this again. This is not a very helpful separation, but we'll go down to RTL and look at top here. So the UART TXT when that goes high is where we're going to see things changing. And so we want to access, let's look at this, the clock. C data. Generally not touched by application code. Okay, well, we can access the Yeah, so it's really saying like the interface we have to it is the top module. So that is pretty interesting. I think we probably should look at the parameters. So what I'm thinking about right now is that in our receiver, we have our cycles here, which means that to do anything, right, we have to click that, we have to take the clock 10416 times, so 10,416 times to get our baud rate. And we don't want to do that, right? We'd prefer that we instead, we're just able to do once. So we want to set this as a parameter. So let's look at Verilog parameters. So parameters are Verilog contracts that allow a module to be reused with different specification. And I know you can set these in Verilator as well. And you can have default values. Design top. Verilator set parameters. That's not what we're looking for. All right, so we have our local param here. This doesn't really help us too much. Let's see if there's anything about parameters. All right, well, let's go ahead and set our parameters first, and then we can fix up how we set them later. And I'll close this just so it's less confusing. Okay, well, it is already set as parameters cycles. So let's take a look at this again. So we already have it set as a parameter, and so we should be able to instantiate it like this. So let's look at we'll say UART RX dot cycles, and I think that's the syntax. Dot cycles, and we'll just say 1. Oh, well, one thing we could do is, so I guess we'll need to set it at top, perhaps. Parameter cycles equals, actually, let's go to the UART Yeah, I don't know if we have to bubble it all the way up to top. If so, that's kind of annoying. but let's just keep going with it for now. $10416, I think, is what we said it was. Let me double check that. Yeah, 10416. Oops. Okay, and I guess we can just say cycles here. Maybe. We're gonna see if that works. Okay, that seems like it worked. And let's look in our vtop.h. Local signals, data, and send. Is there anything about cycles here? Nope. That's strange. Module parameters can be used to override parameter definitions within a module, and this makes the module have a different set of parameters at compile time. Nice. This looks useful. It looks like it's using system verilog, but let's add this to our docs here. Resources, yeah. Oops. And this was called Verilator. It's embedded Verilator series, we'll say, because this looks like it has a number of things. All right. Getting started. Module AOU parameter width. Okay, so they have a parameter there, which is cool. Maybe they'll use it somewhere in here. Ah, max sim time. Yeah, so they're doing the waveform dumping here as well. And that is, I think, some better syntax there. We can just say 1. Delete here. Oh, that was incorrect. I feel like I need to just do some C++ work on the side as well. Okay, so we are evaluates all signals. Wow, this is a great guide here. Running the test bench. Yeah, GTK wave is what I was going to talk about earlier. Wow, this is a great guide. Definitely going to tweet this one out after this. In fact, let's actually look at our doesn't like this. We really shouldn't be GTK wave BCD range times. We really shouldn't be considering top, I don't think, when we simulate the ALU. So I don't know why I don't have my relative numbers. Let me just make sure that we're actually running this. Okay, yeah. So we must not be actually ticking the clock there. Undo that. Let's see if we simulate.top. Yeah, okay. Let's see if we GTK wave data.vcd. Okay, it's the same thing. All right. Do they set the parameter anywhere in here? Parameter width equals 6. No, I don't think they mess with that at all. Yeah, I've got to get a better workflow for this. UART txd in here. So we want the txd in to go high. Let's try that. tb uart txtn, and we'll just toggle it as well. See what happens there. And yeah, we pass that in. And let's set our cycles to 1 here. What is in our GTK wave here? I don't think we're actually writing anything, so we're probably not flushing the trace correctly. They're not flushing at all, so let's see here. Ah, we're not closing it. So tb trace, tfp open. So we need to do a tfp close. Let's close this. Oh, I don't know what this is about, but let's grab that. VCD times range is equal to 0. Let's see if we can find anything on that. Let's look. TFP 99. So I admittedly don't know what that means here. So let's look it up. Let's see if we can find it in the table of contents here. Trace ever. You can call trace object trace on multiple variated objects the same file if you want all data to land in the same output. Call variated trace ever on true. let's see. So trace 99 levels of hierarchy. So we have a TFP dump here. Context P. Okay, so I think we need a TFP dump, and let's say that it's going to be I, perhaps. And let's start this with 0. Aha. All right. So things are happening. But there's nothing to see here. So signals time. So it's basically saying only time is changing. So let's see if we can make some other stuff change. So let's do printf. Right, we need to actually uart txt in. It's not going to like this, I'm sure. What is the printf syntax? Characters, decimals. Let's do D. Okay. %D. All right, so it's printing some stuff. That's great. Let's actually make it print. New lines. And we want to maybe bring this down a little bit. Let's say 5. And let's instead print TB data, maybe. TB data, which I don't think is going to like this printing. Yeah. He has no member data. So let's look at RTL. Oops. All right. Gosh, yeah, this is not super easy to do from top. Maybe we should do each module individually, actually. But we'll keep trying this and go from there. TB. What do we do with the LED here? Because really what I want to know is as the UART state changing, the receiver, module state changing. So notif is that. Okay, perfect. Actually, notif is going to be very helpful here because we're just toggling it each time. Okay, or not each time, but notif. All right. No member notif. So I must have gotten that wrong. Oh, it's LED 0, I guess. LED 0. Oops. Invalid type C data. Unsigned character. Object directory vtop -h LED 10 is a what is VL alt 8? You know what? Let's just print LED. Zero, 0, 0, 1. So that's interesting. If we look back over at our UART-RX here, so our notif, we set it to 1 when we get the start bit. And here we're saying if n is 1, so let's print them both. Yeah, I've got to get some C++ set up for any of them here. So 1, 0, and if we look back, if we start off so we're starting it at 1, and so it doesn't trigger. And then on 0, maybe we can actually pull a syntax CalDraw here. Yeah, this is interesting. So at 1, it's not sending, so notif is 0. And then on the second cycle, right, we're going, we're pulling it down. And so that calls us to transition. And then in the start bit, we drive it high. So I'm wondering why. Let's play this out a few more. Where do we send it again? We're setting it high for this whole sequence here. Let's say I less than 15. Get a few more data points here. Okay, we're driving it high that whole time. Do we ever drive it back low? Three. I'm guessing that has something to do with the fact that LED is has two different things. Has two different, we have two different LEDs, although I don't know what VL out 8 means. Or I mean, I know it's like a preprocessor directive, but my C++ lack of knowledge is showing through here. Verilated.h. Yeah, we don't have that. That's going to be in the wherever verilator lives. Oops. Include verilated.h. C data name. Okay, so we're getting our name, most significant bit and least significant bit here. So declare output signal 1 to 8 bits. VL out 8. Oop. C data. Verilated var type, aka C data. 1 to 8 bits. Okay, so it's just literally the bit. Oh, okay, so that's interesting. Let's pull it out. So we started getting 3 here, right? Well, we can't really see that now. Let me scroll back up. So we started getting 3. Why did that happen? Well, it's representing it with 8 bits. So we still have up our window here. And so let's say we have our 8 bits here. I'm sure these are not even at all, actually. But let's take these and say we have 8. And they all start out 0. Oops. So these are all zeros. Okay. So the unevenness is making me upset now. But so they're all zeros. And my gosh. Then we have 1 go high, right? And so what we're seeing there when it's printing out is a 0, right? As you would expect. This is a horrible diagram. And then here, right, we have binary 1. And it's an 8-bit data structure here. Oops. Or an 8-bit type. This is C data. And so when the second LED, which is driven by the transaction, or I would say transaction, the transmitter goes high, then we're going to end up with 3 here. So say verilator C data. Make this a little bigger. Maybe we can't make it a little bigger. Nice. I feel like that's actually really interesting. I'd love to post about that after this. I know this is probably not the most interesting thing to folks, but super helpful for me at least. I am going to hop over to our docs here. And data types. Verilator defines data types for signals in a module. Let's jump over here and we'll save, and let's look at our user share verilator include verilated.h, and we'll go down a little bit. Verilated pack data. This is pretty interesting to me. Okay, so we are saying, we can probably just copy these over. Oops. All right. Yank that. Okay. So I think that is pretty helpful. But I want to talk about this LED example. Had a for example, Moss passes LEDs. I want to actually look at the I think there's a controls LEDs on the already A7 using one signal per LED. These are defined as a let's see what would be the proper way to refer to this. Verilog types. I think it would just be a variable. I guess through a wire of width 4. All right, that's a little clunky, clunky with the wording, but I think that gets the point across. Okay. I did want to take a look at VTOP. Let's see, LED. Let's actually look at our verilated. Oops. Include verilated .h and we were going to look at C data. Okay, so this is where we have all of these nets. Yeah, declare output signal. I believe this would be C++ macros. Sure. Microsoft Learn, that works. Yeah, so it's defined. VL out 8 name MSB LSB macro. Which really just creates a I don't know if it looks like the MSB and LSB don't really serve any purpose. Because, well, I mean, I guess we're being more explicit when we declare. But, yeah, I mean, it's just creating the C data type. Instantiates a variable with name, and type C data. Cool. Alrighty. How about we get back to our actual simulation here. So last thing we saw was make simulate.top was giving us this output. So this is actually pretty interesting here. I'm going to change this slightly and say, let's, instead of printing, instead of printing this, let's print I. So 28 ticks of the clock is when it switches. But this makes sense, right? Because we're saying the reason why the TXD would go high or start transmitting is because we will have set the send signal, which unfortunately we can't access. Or did it say that we can't access it, or did it just say that it's typically not accessed? Let's see here. Generally not touched by application code. But it looks like we can if we want to. So, I mean, yeah, let's give it a try. Top.send. Okay. Why not? Oops, TV. Yeah. So here's where send goes high, and we have it there for 2 clock ticks. Okay, so it makes sense, right? Because we're basically doing 2 ticks per each um, operation, because we're on the change is where we're shifting states, right? So when it goes from high to low or low to high. And so it makes sense that we'd have a double, right? And then when we hit send, which would be the first number here, when we hit send on the last part of this, so let's jump over here and look at our UART RX here, and let's look for send. When does send go high? At the very end. Here we go. Cleanup. So we're going to hold it here for a cycle, and notif is still high. So what we're seeing here is LED, which is notif, is high, and send is high for these two. And then it goes back, and if we actually came back around, so let's say we wanted to, I'm just like practicing my Vim here, but let's say we find 50 and we replace it. It doesn't actually highlight it. That's kind of annoying. 50 and we replace it with 100 here. Oops. Let's see if it transitions twice. Yeah, we send multiple times. So that's kind of neat. So let's see, I want to try, let's say that we want to say if tb dot top dot send does not equal 1, then we want to do this. Otherwise, we just hold it steady. Or rather, what is it when it's low is the question. We want to hold it at 1. Okay. UART txt n equals 1. So toggle it until we hit send and then just hold it at 1. Okay, cool. Yeah, and then saying we're just gonna sit here, and then we send. We assert send, and that causes the transmitter to start sending. Let's actually make this a little easier. So send, and this is LEDs, and we'll say what do we actually want to see here? We want to see the oh, we could be getting the state. Yeah. Okay. So we really want to see the UART RxD out. Yeah. UART RxD out is what we want here. Take that. And we'll say, oops. Oops. TV. All right. So our UART out appears to go high, which means we're not sending, right? So let's look over at RTL UART. Yeah, so our out is high until we get send, and then we go low. But it looks like we never go high after that. Which we should at least go high for out. And let's jump over here and say, take this and in 6B. Just add this in here. Oh no, it needs to come afterwards. Okay. You are in %D. Oops. TXT. That's a helpful error, actually. Do I have these flipped? Yeah. Okay, so we're driving it high. Then we hit send here. And we go to 0. And so maybe we're getting stuck here. Does our LEDs go high? So send, go high, start setting LED to 1. Out, though. Okay, out goes to 0. And then TX data bit index. W. Okay. So we're staying in data bit, and we're saying we need to go through each of the bit indices. Huh. We're setting our clock count to 0. At the top here, but I think this should be going in. Let's see if this was changed in our PR. Data bit. Okay, if we're less than the cycles, then we keep sending, we stay with the same bit index. If bit index is greater than 0, we decrement the bit index, set clock count to 0, and then that still seems right to me. And we should be getting far enough along that it actually changes too. Oh, I know what the issue is. We didn't set the cycles. Yeah. So we want to take this guy and put it here. We're still saying hi though. Wait. Also, our URN is toggling. We get to send. Okay. Yeah, I see. Still, it shouldn't be impacting. UART out 1, 0. Okay, so we actually are changing UART out now. And we really should be saying drive it low, and then our start bit, and then what are we saying? 1, 1, 1, 1, 0. Let's see what W is in ASCII. It's capital W. 0, 1, 0, 1. So we go high here. Start bit. Zero. One, one. So it should say, oh no, okay, so it starts, when we're in idle, we should be sending ones, right? Okay, so here is our start bit, or sorry, here's our first in idle, and then we move to our start bit, and then we're saying 1, 1, 1, so the lower bits of W here, 0, 1, 0, 1, 0. So here's our 6 ones, so representing 3, 0, 1, 0, 1, 0, and then we go back to just idle. So that looks good. Because, yeah. Oh no, sorry, idle is low. Why, when we're sending... No, sorry, idle's high. Okay, so this looks good, actually. Also didn't realize we'd been on here for 2 hours at this point. Let's try and actually use our input data here. And see if we we'll take our it's just data. Oh yeah, it's not considering the when we run simulate. We'll just do it again. All right, hi, wait, and then send. Start bit is low, and then just zeros to 1. Well, we can access data here, I believe. Top.data. Let's see if I can do some C++ here. Auto stop equals false. And not stop. And then here, let's say stop equals true. Is this C++? Hey, it seems to. Okay, so we're toggling it. Still seems to be all zeros. So let's actually maybe if we look at what if we took this and this? Oops. And cycled it twice. Oh my gosh. That's not what we're doing. Include bit set. Let's say let's do %x for those. Data. Can you do a, let's see. Like a 2D. Does that work? Nice. Okay, that is very helpful. Okay. So we're not duplicating anymore, so that's nice. So we say, okay, we're ready to send. Start bit. And so AA, we should be sending a 0 first. Send. Start bit. We're sending a 1 though. And we should be sending the least significant bit first. So 1 0 1 0 1 0. That makes sense, right? Because we were just toggling it. Okay, so it does appear that we are actually sending the value back, though. Perhaps in the wrong order. But so that's positive. I feel like we got a pretty good look at it. I think there's a few things clear here. One, I want to do some C++ practice, probably just stream that as well. Also, of course, welcome any feedback from folks on how to be more efficient here. But yeah, overall, I actually feel pretty good about our progress here, especially the investigation into the variated header file and looking at the C data type and how it's using the packed data types to represent the signals. That's pretty neat. Yeah, so cool. I think that's probably going to be a wrap for today. I think we are, let's see, about 2 hours and 15 minutes in. I'll go ahead and switch back over. So thanks for tuning in. I know it's a little bit of a more painful one today. And we didn't actually get to doing anything on our actual dev board here. But I appreciate folks tuning in. We're going to keep making progress, keep struggling along with things. I do hope to do a little more prep before the next one, because I was a little all over the place, instead of kind of like having a game plan for tackling. So I think we were a little inefficient today, or I was a little inefficient today. So I appreciate y'all bearing with me. But maybe I'll find a little time tomorrow to be able to stream as well. But I really appreciate folks stopping by, and I hope everyone has a great rest of your weekend.